Next, we have Professor Jonas, chairman of the Department of Ophthalmology at the medical faculty, Mannheim of Heidelberg University, and academician of the German National Academy of Science, Leopoldina. His topic is myopic axial elongation, anatomic finding for its better understanding. Please.
Dear Professor Chang, dear Professor Lam, ladies and gentlemen, it's a great honor and pleasure to be here. The by far most important risk factor for the development and progression of high myopia-associated complications, which is myopic macular degeneration, and high myopia-associated glaucomatous and non-glaucomatous optic neuropathy, is longer axial length and further ongoing axial elongation. If we want to prevent the development of the complications and their progression, we should try to stop axial elongation, and for that, it is helpful to better understand how it occurs, how the eye becomes longer. The process of axial elongation may be considered to be part primarily of the physiological process of ametropization, where after the second or third year of age, when the eye has up to that point grown spherically, the eye just only becomes a bit longer to adjust the length of the optical axis to the given optical properties of cornea and lens. And an overshooting of this process of ametropization would be myopization. And I would like to present you a hypothesis how it may occur, but this is similar to a house of cards, and if there's only one finding wrong, the whole hypothesis will collapse. The question is, what can we clinicians learn from what we see and may detect every day to put it together like a puzzle into a model to understand why and how the eye gets longer? The hypothesis is that the tissue which makes the eye longer, and that is one of the primary questions to understand the process, the tissue which makes the eye longer is Bruch's membrane, and that the eye gets longer by a retina-triggered localized enlargement and growth on Bruch's membrane in the mid-periphery, with the maximum at the midpoint between the equator and the posterior pole. And I would like to list some anatomical findings which speak in favor of that hypothesis. First, without doubt, the choroid in the subfoveal region gets thinner with longer axial length. If the sclera would be the tissue which makes the eye longer, the choroid would become thicker because the sclera would move away from Bruch's membrane. The fact of the subfoveal choroidal thinning implies geometrically that the posterior pole of Bruch's membrane moves backward more than the posterior pole of the sclera, so that the netto effect is a thinning of the choroid. As we know, the sclera gets thinner, most marked in the mid-periphery, less at the posterior pole and almost not at all anteriorly, speaking in favor of the mid-periphery as the region where the eye gets longer. And just to show this example where we see in this highly myopic eye that the sclera foveally appears to be quite thick. Also, the scleral volume is independent of axial length, so that all changes in the sclera are just a rearrangement of the available tissue and not an active growth. The same with the choroid, where the choroidal volume is independent of axial length. In contrast, the volume of Bruch's membrane increases with longer axial length, since its thickness is independent of myopia. An extremely highly myopic eye has a normal thickness of Bruch's membrane at the posterior pole or somewhere else, speaking in favor of an active growth or volume increase of Bruch's membrane. Only in eyes with a secondary type of high myopia due to congenital glaucoma, Bruch's membrane thickness decreases. Addressing the question whether Bruch's membrane may be strong enough to give some biomechanical strength to the eye, clinical observations show that in the regions of colobomas, where there is no Bruch's membrane, one often finds a localized scleral staphyloma, as if Bruch's membrane is the most important structure to give form and shape to the eye. The same finding one can get in eyes with acquired defects in postmembrane, as in this example with toxoplasmotic scars. The choriocapillaris, its density also was found to be independent of axial length, fitting with the observation that postmembrane itself was independent. The density of the RPE cells at the posterior pole also was independent of axial length, but decreased in the mid-periphery, fitting with the notion that in the mid-periphery postmembrane grows, leading to a decreased density of the RPE cells, but that postmembrane in the macula is untouched. According to the condition for the process of ametropization, no compromise in the density of the photoreceptors. Also, the retinal thickness in the macular region is independent of axial length, even in highly myopic eyes, but decreases in the mid-periphery, where also the photoreceptor density decreases, fitting with the notion as if the underground postmembrane gets wider. Now we know that with increasing axial elongation, the disc becomes vertically oval and gamma zone enlarges, almost compensatory to each other. It may be explained by a shift of postmembrane opening into the temporal region, as shown in the lower part of this figure. And that again could be explained by a growth of postmembrane peripheral to the optic disc, leading to the shift of BMO in direction to the fovea. And as we can see here, after 10 years of follow-up, the distance between the disc and the fovea has increased by the green bar, and simultaneously the size of beta and gamma zone has increased by the same size, so that the axial length associated elongation between the disc and the fovea, as shown here, is only due to the gamma zone, so that the length of the horizontal postmembrane, that means the distance between the fovea and the start of gamma zone, is independent of axial length. Again, fitting with the notion, no compromise in photoreceptor density, and accordingly the choriocapillaris density and RPE density were independent of myopia. Now, is postmembrane indeed strong enough? In this kind of experiment, it can withstand a pressure of 80 to 100 millimeter mercury, making it about 100 times stronger biomechanically than the sclera in relationship to the thickness. So that the notion is that up to the second year of life, the eye grows spherically, then it just gets a bit longer to adjust the length of the optical axis, which ends at the photoreceptors, to the given properties of the cornea and the lens. This could explain the change in the eye shape. It can explain, as pointed out before, the decreased photoreceptor density in the mid-periphery where postmembrane becomes larger. It can explain the phenomenon that some eyes, particularly myopic eyes, have a displaced foveola in relationship to the posterior pole, because there could be an asymmetry in the growth of postmembrane between both sides of the same plane. And it could also explain the development of macular ridges, a prominence in the macula in one meridian but not in the other, where may be an asymmetry in the growth of postmembrane between two sections, between two planes perpendicular to each other. And very theoretically, a staphyloma might be explained by a localized overgrowth of postmembrane leading to an outpouching. And finally, even the maculoschisis, taking into account that the inner limiting membrane as a basal membrane is not elastic and is fixed to the optic disc. Postmembrane, shown by C, can slip backward if there's a larger circumference, so that inside of the retina in the macular region, a tension may occur leading to the maculoschisis. So that, again, this is just a hypothesis based on anatomical findings, and one is looking for counter-arguments destroying this whole house of cards. Thank you very much.
Thank you, Professor Jonas.